All right, good morning everyone. Welcome to this afternoon session. So we will start with the first part of a three-part lecture by Benjamin Huard. So Benjamin is the lead of an experimental research group at INS Lyon in France. And his group focuses on the study of continuous measurements and feedback on the experimental platform of superconducting circuits. So Benjamin, the floor is yours.
Yeah, thanks a lot, Pierre. All right, so it's a pleasure for me to be here. Thanks a lot to the organizers to having invited me to this very nice event. So this will be a three set of lectures, and my goal is to provide you with the basics and the basic understanding of what makes superconducting circuits a good platform for quantum trajectories exploration and feedback control. And so since you already had the lecture of David DiVincenzo, I will start. So this way should not take too long for today. And then we will discuss together how to describe the measurement apparatus and their modeling in this kind of experiments. So namely the homodyne, heterodyne detection, the amplification at the quantum limit, and photon counting. And then we will discuss let's say the state of the art in the experiments on how to the statistics of quantum trajectories and feedback control. Okay, so let's go for it, right? So you saw already maybe with David DiVincenzo that for a variety of reasons the typical frequencies of operation of superconducting circuits are in the microwave domain. So these are around, let's say, a few gigahertz. The main reason for that is that we're using aluminum junctions, and the superconducting gap of aluminum is, let's say, twice the gap is about 80 gigahertz. So we need to be much below that with the frequencies in order to not to excite quasi-particles and disrupt the nice properties of coherence that superconductivity brings. So this sets, let's say, a limit to below 10 gigahertz if we stick to using this kind of superconducting elements. And so if you look at the typical values of what's epsilon naught and what's mu naught, you get that the right order of magnitude to get gigahertz frequencies is to have geometrical objects of millimetric extent. So this is very easy to fabricate, millimeters. We can do it with a very conventional nanofabrication equipment. And so basically this gigahertz domain, it lives in the realm of electronics. And after that there's the terahertz gap where we have very limited tools, and then there's the optical regime. So in electronics we have a variety of instruments that we can use, which are very different from their optical counterparts, but somehow there is always some correspondence between these components and the more known optical parts. So for instance, this directional coupler is similar to a beam splitter in optics. There are circulators that break the reciprocity in the propagation of waves, which are similar to Faraday rotators. But what really is fantastic with these RF instruments is that we can very easily connect microwave cables to these components. So this is a bit like optical fibers, but the link to the microwave to these microwave cables is much more robust than the link to an optical fiber. So and then there are many commercial instruments which in the past were developed for radar and telecommunication applications, but more and more these the industry of these microwave equipments is making equipment directly for quantum technologies, and so we benefit from a large investment in this, and so from very advanced control instruments and measurement instruments. Okay, so now there's in order to be in the quantum regime for free, ideally we want to place these quantum systems in an environment which is at a temperature which is much smaller, the energy, thermal energy KBT, much smaller than the energy of a single photon. And so in the optics, in the optical domain, you see where the energy of a single photon, once converted into KBT, sits about here, you know, at maybe 1,000 Kelvin or so, a few thousand Kelvins. So it's for free that at room temperature, the quantum optics table like this sits in an environment which fulfills this property. And so since this constraint is fulfilled, doing nothing, just turning off the light in the room, the optics modes are directly in the vacuum, and there's not much more to do. In the gigahertz, in a few gigahertz mode, you see it's well below the room temperature limit, and so we need to use commercial equipments, which are called dilution refrigerators, like in this picture, to reach an environment at a temperature of about 10 millikelvin. And at 10 millikelvin, indeed, a few gigahertz is well within this constraint. And so, likewise, by just thermalizing to the environment, it's for free at these temperatures. And so it's not for free; it's for 400 kilo euros, let's say. So that we reach, you know, this constraint. Okay. So the quantum objects on which we are going to work. So we are saying that these are superconducting circuits, but for real, it's actually the microwave modes. So these are really the fundamental elements, so microwave modes. And it turns out that they are hosted in superconducting circuits. But microwave modes can exist in various shapes, so they can travel freely in vacuum. They can also travel in microwave coaxial cables or in a coplanar or a microstrip like this geometry. So there are various geometries on which microwaves can propagate. And if we now cut this cable in two pieces, this element will resonate at a few discrete resonant frequencies. And we can construct like this superconducting devices, because something we have for free at these temperatures is that many materials like aluminum are superconducting. So we can construct metallic, so superconducting even geometrical structures, either on chip, like this coplanar waveguide resonator, or in 3 dimensions. These structures will resonate at a few gigahertz. So you see this rectangular cavity here, it resonates at about 8 gigahertz, for instance, for these dimensions. And these modes, they will be really high Q. So by really high Q, I mean that we can reach, you simply take a piece of aluminum, you drill a hole like this, and you close the 2 parts, and you get a quality factor of 1,000,000 without much more work. So this is really impressive. So we can get even larger quality factors with more advanced structures. And what you already saw with David DiVincenzo's lectures is that the fundamental modes, but actually any modes of these resonators, can be described as a single LC oscillator, which we can quantize into a harmonic oscillator. Okay, so this is how we build linear harmonic oscillators. But if we restrict to linear oscillators, it's impossible to prepare interesting quantum states. Actually, if you use a commercial instrument to drive a linear oscillator, and everything is linear like this, the class of states to which you're really restricted to work with is the coherent state class of states. So it's, for instance, it would be impossible to prepare the Fock state 1, so 1 photon. So to avoid that, we need a nonlinear element. And in superconductivity, the nonlinearity is provided by, it can be disordered superconductors, but more generally what we're using is a Josephson junction, so a tunnel junction between 2 superconducting electrodes. And the Hamiltonian of the junction is almost like a harmonic oscillator, but in fact the phi squared over 2L, if we look more closely, it's a cosine. So at the bottom of the well, it looks like a parabola, this potential of a cosine, but actually it's a cosine. And because of that, the transition frequencies between each state get lower and lower as we climb up the ladder. So this superconducting qubit is defined by the first two states, the 0 and 1 photon. So the 0 and 1 states are 0 photon and 1 photon in this resonator. And because it's harmonic, if you're careful enough in not changing the drive amplitude too fast, then driving close to omega naught, it will be impossible to climb up the ladder because the drive will not be resonant to any of these transitions. So that's effectively this harmonic oscillator with an infinite number of states is restricted to the first two states. So this is how we build the superconducting qubit. And the Transman regime, the regime of the Transman, which is so successfully implemented in many labs and companies in the world, is the regime where this parameter EJ is more than 40 times larger than the typical energy scale of the capacitor here. Okay, so what happened in 2004 is that at Dhar they reached a level where they coupled a Transman, a superconducting qubit actually, not a Transman yet, but a superconducting qubit to a resonator, and so therefore mimicking the coupling between an atom and a cavity in cavity QED. And so this was the birth of circuit QED, which is really the tool that we're going to use in this set of lectures. Okay, so there are two main regimes with which we can use these two elements. So one is the strongly anharmonic regime, where indeed the anharmonicity, which is by how much the frequency is diminished each time we climb up the ladder by one step. So when the harmonicity is much larger than the dissipation rate, we are really in this qubit regime I just mentioned, we're restricted to the 0-1 manifold. In the opposite case, where this anharmonic oscillator is strongly coupled to the environment, by that I mean that the dissipation rate to the environment is larger than the anharmonicity. And then this is a weakly anharmonic regime, and this one is used for instance, to build parametric amplifiers that operate close to the quantum limit of amplification, so that add close to what quantum mechanics tells us we need to add during the amplification. So there are these two nice regimes. So the first one has been explored in quite many directions. So by complexifying the circuit a bit, you see we can add an inductor, for instance, but other circuits had two inductors, two capacitors, two junctions. So we can play with this, but only with the three parameters, so EJ, ER, EC, so the three energy scales, we can build a kind of a Mendeleev table of superconducting qubits, which each have their advantages and inconveniences with respect to some tolerance to noise, some tunability, or simply decoherence, good decoherence or control. And so here is this kind of one of the most recent version of this kind of Mendeleev table. And if so one of the reasons why it's a very good platform to explore quantum trajectories is that the coherence times and the lifetimes of these systems are getting better and better every year. So this is an updated plot of the decay and decoherence times of superconducting qubits as a function of the year, and you see it's in log scale, and so indeed it's been increasing quite impressively over the last 25 years now. Yes?
So you said without the nonlinearity, it's equally spaced, the cavity modes are equally spaced, but yes, you're at sufficiently low temperature. So then even then you should, only the lowest level should be occupied, right? If temperature is much smaller than. But then you said it's a coherent state.
Yes. So indeed, if you start from the vacuum state and apply only drives, so driving Hamiltonian from microwave sources or lasers, the only states you can reach are coherent states. Now, if you want to put temperature in this story, so then indeed we would need to start from a Gibbs state. A Gibbs state would be a state which is, so you would start from the state exponential minus h over kbt divided by the trace of that. So you start from there. So then indeed, then indeed you would start from a mixed state which has less and less occupied states. So this would be the Boltzmann distribution, right? Essentially, and so the Boltzmann factor between each two, and so then starting from there, if you do this plus drives on top, so a drive would be characterized by a term which is like that. So so the Hamiltonian would be the edge drive would look like this. So if you only are allowed to have one function epsilon d of t, and you start from there, then you will enter you will end up in a displaced Gibbs state after some operations, but that's it. So so if it's linear, even if there is some thermal environment, you will still be limited to let's say bad coherent states.
But why do you want to drive?
Why do we want to drive? So, well, to do some control, right? So if I do nothing, I mean, it will stay.
No, but if at least you have only one level occupied, right? Even at
yes. So at.
But it's almost in a pure state.
Yes. So are you saying that at least this ground state is occupied?
If you want to populate both levels, then you have to drive.
Yes, exactly. Yeah, exactly. Yes. Yeah. All right. Yeah, thanks for the question. Are there other questions? Okay. So all right. So on the flip side, so if we use this weakly anharmonic property, then we can build these amplifiers, and there are many kinds of amplifiers. I will describe in more detail what's an amplifier and how to theoretically describe an amplifier. But just to give you a picture, so these are degenerate amplifiers, non-degenerate amplifiers. So these are for instance, good for phase-sensitive amplification, phase-preserving amplification. And lately, there has been quite a bit of work on what's called traveling wave amplifiers, which are really broadband and close to the quantum limit amplifiers, or even directional amplifiers, which break the reciprocity and allow to amplify the signal without affecting the quantum systems back, except from the desired measurement back action. Okay, the other advantage of this platform is that it can couple well to many quantum systems. So for instance, Rydberg atom with which were actually the pioneered system with Serge Haroche Nobel Prize that recognized this. The NV centers, for instance, or other spin systems, quantum dots in nanotubes, magnons, mechanical resonators, propagating phonons. So all these can couple to superconducting circuits. Okay, so concretely, this such an experiment works like this. So we start from a chip, either in 2D or a 3D resonator, as I mentioned. Then we put it in a magnetic shield at low temperature. This is anchored to the bottom stage of a dilution refrigerator. And so it will be at 10 millikelvin if we do the connection right. Then so this is the picture of the fridge. We close it up with a thermal radiation shield at 10 millik, another one at 1K, and one at 3K, one at 50K, and finally the outer vacuum can. So all this to tell you that these quantum systems, they need to be really well isolated from the environment, the actual room temperature environment. And this is how we do it. Yeah, please. Yes, yeah, so the interest of so it really depends on the experiment. So 3D cavities have historically got much better quality factors than 2D. So for longer lifetimes, it's better to use a 3D. Now for flexibility in tuning the couplings between systems and the design, it's much more efficient to do it in 2D. So depending on on what you want in the experiment. Yeah, it's a good question. So in 2D, so for instance, it depends a bit on the geometry you pick, even in 2D. So if I do a zoom in here of this coplanar waveguide resonator, so this the typical line is so this is metal, okay, and so if I do a cut like this, a cross section, so there will be the substrate here, which is typically silicon or sapphire. Then there will be the metal is like this, right? So the feed lines they do get a bit out of plane. The feed lines are like this, but okay. So they do get a bit out of plane. This is in a vacuum, so it doesn't affect at all the quality factor. Silicon is an excellent, very low loss material, so it's still okay. It starts with the level of coherence times that is now the state of the art. It starts to be limiting. But what really is bothering us is the fact that these fields C, and so there's a participation of all the defects, all the material that we didn't clean well enough on the interfaces. So these are the mostly annoying ones. And yes, but so in 3D it's very different because most of the field is in a big volume of a vacuum, and so that's the quality factor is better. Okay. Yes, and then we hook up these quantum systems with microwave cables that go down to or up to commercial hardware. Okay. So to manipulate these systems to make quantum control. So the most simple ones are very easy to do. So if you want to do an operation that goes from the ground to the excited state, what you need to do is send a microwave pulse at the resonance frequency of the zero-end transition for an amplitude and a time which are such that their product provides exactly this rotation in the Bloch sphere, 0 to 1. If you want to do half of that, so just stop at the equator on the Bloch sphere, then you provide, for instance, half the amplitude with the same time. And it's even possible to choose the phase of the superposition by changing the phase of the drive. Okay, so you see it's as simple as this. One can also do rotations around Z by changing, by putting some detuning in this drive. So you see there's a full control of the Bloch sphere. So single qubit operations are simply done by microwave driving. For the readout, so we're going to discuss that in much more length because this is at the core of quantum trajectories. But the system of choice is the one that David DiVincenzo ended up with. So it's a transmon qubit, or more complex, but let's say a qubit, coupled to a resonator. So the circuit QED architecture. And this one is done in such a way that the frequency of the resonator depends on the state of the qubit. And so then the readout of the qubit comes down to sending a wave at the readout resonator, or close to the readout resonator frequency, and measuring what's coming back, and in order to reveal what's the frequency of the resonator and hence the state of the qubit. But again, we are going to discuss that in more detail. Just to give you the state-of-the-art numbers, so single qubit gates these days they are as good as so they do a 2⁻⁵ errors per gate in less than 10 nanoseconds. So this is a record number. So you see it's a very low error rate. And 2 qubit gates are in the range of 10⁻³ errors per 2 qubit gate. And the readout, which we're concerned with here, is so last year it was 2 × -3 hours per readout. I think last week there was a paper by the Yale group that reached below that. Yeah, so this is the state of the art. So you see really good numbers. So to explore quantum trajectories, this is really good numbers. To build a quantum computer, this is at threshold essentially of quantum error correction, or a bit better than threshold now. Okay, so let's look more carefully at the readout process. So the Hamiltonian that I think the last Hamiltonian you saw with David Vincenzo was the James Cummings Hamiltonian. So it was a coupling. So maybe I should write 1 or 2 lines about this. Is there? Okay. So the James Cummings Hamiltonian is so what are the notations here? Okay, A dagger sigma z. So A dagger sigma minus plus A sigma plus. Okay, so this is the coupling term in James Cummings. So what one can do from there is recognize that because of this coupling, the modes, the qubit mode and the resonator mode, become a bit hybridized because they're coupled. And if we write new operators recognizing this hybrid nature of the modes, so we have essentially a new A prime and a new sigma prime mode, if you want. This one is mostly cavity-like, but it has a bit of qubit part. So it has a qubit part which has a probability G over omega omega cavity minus omega qubit squared. So this is the probability that this new mode is actually a qubit localized in the qubit part of space, and close to 1 if the detuning is large enough to be localized in the cavity state, and reciprocally sigma prime would be mostly localized in the junction, so in the qubit, but a bit in the cavity with the same probability. So with these new operators, if you do the calculation carefully, you will end up in this new Hamiltonian. So the transverse coupling, the James Cummings coupling, is now transformed into another coupling, which is called the dispersive coupling, and you see that that it's a very different form, right? So now the coupling is such that it's the product between the qubit occupation times the number of photons in the cavity. Okay, and we still have the bare cavity and qubits, but remember that no, these are not exactly the cavity and qubit modes, but a hybrid version of them. Okay, so here I'm going to show you data that an experiment we did more than 10 years ago now. So this was a 3D resonator coupled to a qubit, transmon qubit. The cavity was about at 8 gigahertz, the transmon at about 5, and this dispersive coupling rate, so the chi in this coupling term was 4 megahertz, so much smaller. Okay, so if we reorder a bit the terms, you see that we can write the Hamiltonian as a bare qubit term plus a term which is the resonator, and the frequency of that resonator you see is the bare frequency minus chi over 2 sigma z. So this is precisely this term that tells us that the cavity will shift by chi when the qubit changes of state. Okay? Yes? So the qubit, so yes, thanks for the question. So you see this is a cavity which is about 40 millimeter long. The qubit is sitting so maybe you see barely a rectangle here. So this is a transparent rectangle of sapphire, and on top of the rectangle there's a Josephson junction in the middle, connected to 2 antennas which have a few millimeters in length. So this is called the 3D transform. Yeah. And this is a picture of a junction. So you see the scales are very, very different. But the antennas are huge. The antennas are huge. This is really a quantum object that is macroscopic in size, right? Quantum mechanics is absolutely not for reserved to atoms or the infinitely small. It's really it works on millimeter scales. Okay, so yeah, so now the question is how do we characterize the signal that is measured in order to infer what's the qubit state? So we would get so let's say we send a signal close to the cavity frequency on one side, which is poorly coupled, let's say, and then we look at the signal coming out. So something that's nice already with this architecture is that we can channel the signal into one microwave cable of our choice. So preferentially the one to which we attach the measurement setup, and so it's possible, you see, to channel both the readout signals, but as you will see in a later talk, we can also channel out the dissipation, the spontaneous emission of the atom into a port of our choice, and so measure it. So this is one really interesting aspect of these systems. And so if we look at the voltage that we measure, the voltage is so let's say the voltage will be so if we treat it classically, it will be a sine function, which we can decompose in two quadratures, I and Q, the cos and the sine components, right? So I and Q correspond to the Hermitian and the anti-Hermitian parts of this outgoing quadrature, and so now we can plot this. So let's say we start from the vacuum state, so we don't drive, but we still measure. Here what I plot is the variance. So let's say this is the distribution of quadratures that we will measure if we were to repeat an experiment where we measure many times these two quadratures, and so what we would get is a Gaussian function. It would be a Gaussian distribution in 2D, and here I plot the contour of let's say at half width, and so this would correspond to what's called sometimes the half a photon of vacuum uncertainty. So here you see directly the 0-point fluctuations, which are revealed or actually are defined by the variance of the signal you measure if you repeat the experiments many times when measuring the vacuum. Okay, so for now it's still vacuum, but maybe 5 slides from now you will define the measurement rate. So now let's say instead of sending the vacuum state, we are going to send a coherent state now. Okay, so we are sending a drive. A drive corresponds to a displaced vacuum state, so it's a coherent state, yes. And so this is the distribution that we would get, right? So the length of this lollipop corresponds to the square root of the number of photons, or the amplitude of the coherent state, and again we still have this the variance corresponding to the vacuum uncertainty. So this would be at the input, but then at the output, what we're going to see is the following. So if we change the frequency of the drive we're sending, and we measure the phase of the average amplitude we are getting out, this is what we see. When the qubit is in the ground state, we see a 2-pi phase, a pi phase shift, which you can see here. And if the qubit is in the excited state, we see the pi phase shift, but displaced in frequency. So the point at which this pi phase shift occurs corresponds to the frequency, the resonance frequency of the cavity. And as you can see, indeed, when the qubit changes of state, both are shifted by chi. So how do we measure the qubit state? Well, what we're going to do is send this incoming wave. We're going to send it at the middle frequency, so here in between. so that when the qubit is in the ground state, we will have a phase which is here positive, and when it's excited, we would have a phase which is here negative. So, so the field coming out will now look like this. So when we do an experiment where the qubit is in the ground state, we get a lollipop which is now shifted to upward, so towards positive imaginary A. And when it's in the excited state, it will be shifted downward, right? So this is the measurement outcome. And so indeed, by measuring the imaginary part of A out, so this the vertical quadrature here, you see that we indeed get a strong and QND measurement of the qubit state. So this is not unlike what let's say the traditional known setup of Stern and Gerlach. So you see, if we want to do the analogy, so in Stern and Gerlach, there is a spin connected to a silver atom. So the spin is the quantum system of interest. It is connected to the position of the silver atom. So let's say the position along the z-axis is enough. And then we send this atom into a gradient of magnetic field. And depending on the state of the spin, this degree of freedom, so the position along z, will be shifted to upward or downward, leading to two possible stains on the screen, which correspond to a spin up or spin down. And so you see, this is very much like what we have here. So instead of sending atoms, we're sending electromagnetic waves. We are so the equivalent of the gradient is the coupling, the dispersive coupling between the qubit and the cavity. And at the output, these two uncertainty disks correspond to the two uncertainty probability distribution, the two probability distributions we have in the quadrature measurement when the qubit is in the ground or excited state. Okay, so this is the experiment we did. So here we prepare the qubit in the superposed state 0 plus 1, and we measure. So we integrate the signal for some time, and here I show you the result of this integration referred to the intra-state of the cavity. So again, the two quadratures, and you see that we place here a threshold in color to distinguish the states that, so the measurements of the reflected field that correspond to the ground state and those that correspond to the excited state. So instrumental in this experiment is the use of a quantum limited parametric amplifier right at the output of the outgoing mode. Otherwise, everything will be blurred and convolved by a very big Gaussian curve. So here you see we can distinguish these two peaks rather well. So if we prepare now the qubit in the ground state only, this is what we measure. If we prepare the qubit in the excited state, this is what we measure. Okay, so you see we have a good pointer state, and so what we can also show is, for instance, trajectories. These are not quantum trajectories; these are measurement records. So here we prepare the qubit in the state 1, start the measurements of the quadratures, and here I plot the imaginary part of the outgoing quadrature we measure as a function of time. And you see it starts above 0 because we prepared in 1. And at some point in this measurement record, it goes down, indicating that now it decayed. So we can repeat this experiment many times, and of course this is stochastic, right? So each trajectory is different from the other. Some of them go back up, so meaning that there are thermal excitations that are also happening. We can do a statistics of the time, the first time at which it went down, and so if we plot this histogram, we see a nice exponential decay, which reveal the decay rate, which was here 26 microseconds. But again, this was more than 10 years ago. Okay, so what's beautiful with this setup is that it's very simple to answer a question, to tune the measurement strength. So you see that if So similarly to the Stern-Gerlach experiment, if we in the Stern-Gerlach, it would correspond to diminishing the amplitude of the gradient of the field in the region where there are the magnets. So here, what we do is we send a field of a lower amplitude simply. So if we send a field of a lower amplitude, the two uncertainty disks will now overlap. And in this case, if we measure in one experiment, if we measure a point here, if we measure a set of two quadratures that are here, we don't know for sure whether the qubit is ground or excited. And most importantly, because not only we don't know, but nothing in the universe can know, the system is not collapsed into one of the two stages or E. It is actually updated. It's still a quantum superposition if we start it from G plus E, but it's updated to a new quantum superposition. Okay.
So you're measuring the phase, is it the engine? So this and why is it continuous?
So what we are measuring is this I hope I'll get in much more detail today. So what we are measuring is let me go back again. What we are measuring is the voltage at the level of this amplifier. Turns out that this voltage can be decomposed into two quadratures, I and Q, which correspond to the Hermitian and anti-Hermitian part of A out. So what we're measuring are two real numbers, okay, which at each time step of that the voltmeter, which is an analog to digital converter, at each time interval that the ADC allows us to acquire, we extract two real numbers corresponding to these two values, and so one point in this phase space. So when I plot these measurement records, which you say are continuous, so they're actually made of points. Each point corresponds to one time interval. So here, I think it was maybe a microsecond. If I'm, yeah, it may have been. Oh no, yeah, it may have been a microsecond. So every microsecond, if you want, we plot one quadrature. We plot one quadrature. So yeah,
what is 1.8 photons?
So here so we send a drive on the resonator, which is such that at any point there is an average 1.8 photons in the resonator. So the square of the coherent state is 1.8. Well, I would say I would claim that nothing is continuous, but yes, we can model it by continuous. So what's discrete is that ultimately, and this is something I think we should rediscuss when I will introduce more carefully in the part 2 the measurement apparatus. But you will see the discreteness appear very clearly. I hope. Yes. Okay, so yes, and to answer your question about the measurement rate, so we can tune the measurement rate by driving more or less strongly by changing the amplitude of the incoming drive. But to quantify it, so the measurement rate is simply the loss rate of the cavity times the distance in this phase space squared over 2. So this is the measurement rate. If this quantity tells you essentially what, so it tells you by how much the qubit gets dephased, what's the dephasing rate of the qubit induced by the measurement. So if I just send this amplitude towards the cavity and look away, I don't record the measurement, the qubit will get dephased at that rate. If I do a good job at very carefully amplifying the signal and measuring it, I can get that much information per second. So the number of bits per second will be gamma m over log 2 if I do a perfect job. Of course, this won't happen, and the difference between the perfect job and what I actually get is called the quantum efficiency. It's between 0 and 1. Okay, so to tell you, so to show you a bit, so something related to measurement, so the Zeno effect, right? So it's possible to see a Zeno effect on Rabi oscillations in the system. So these are Rabi oscillations. So ideally they would go around the Bloch sphere forever, but actually they decay if we don't do some feedback or some other mechanism. Now, what's going to happen if I start with these Rabi oscillations and turn on the measurement? So this is an experiment that was done at Saclay in 2010. So they started from you see from a weak amplitude, so a weak measurement rate compared to the Rabi oscillation frequency, and there you see decaying Rabi oscillations as in this picture. But now, if we increase the measurement rate, still without looking the unread measurements, right? We look away. Then you see that these amplitude, these Rabi oscillations decay, and in the end they're overdamped, and it's not oscillation anymore. So this is the effect of. So this is the effect of the Zeno effect on the Rabi oscillations. Another cool experiment with this was done in Berkeley by Côte when he was a postdoc there. So these are the quantum trajectories of a qubit. Yes, question?
I have a question on the Zeno effect. So why isn't it stuck in 0 or 1, like the value corresponding to 0 and 1? Because you are measuring sigma z, right?
Yes, we are measuring sigma z. So they're indeed, so Zeno, so what Zeno does is forbidding a unitary evolution that is slower than the measurement rate. Okay, so maybe let's take a couple of minutes to discuss this, right? So this is the Bloch sphere. Let's say we're in the ground state and an excited state. And let's say you start from here. You want to do Rabi oscillations at a frequency omega. What Zeno effect tells you is that if the measurement rate is much larger than omega, it's a bit in a picture where you were to do one measurement every 1 over gamma m, one projective measurement 1 over every gamma m. It tells you that if you're in this condition, the Bloch vector will have shifted so little that the probability to get back to 1, let's say the probability to jump to 0 is in the square of the angle, because it's a cosine. Right? So because of that, when you sum up all the times, all these small times, you end up with something which is infinitesimal. But what we see here is that there's another mechanism at play, which is that there is on top of that some decay, and this decay at a rate gamma, let's say gamma down. So this decay, the Zeno effect cannot fight against. So it's we are still in a regime where gamma m is much larger than gamma down, but because the environment is large, the characteristic time scale of the memory of this environment is much shorter than this one. So so the characteristic memory of the environment will be this rate will be much larger than gamma m, and because of that, the Zeno effect cannot fight against this, and so it will go down eventually, and so this is what you see. It ends up not on the North Pole.
So one question I had. So the decay rate, then what you're seeing in the graph, is it connected to the decoherence rate?
Yes, indeed. What you see, yes, what you see in the graph is, let's say, to be more clear, the extra damping of these oscillations when I turn on gamma m, when they turn on gamma m, is indeed the measurement induced the decoherence rate. Yes, absolutely. Okay. Yeah. So to go back to Kater's experiment, so this in this experiment, so I think actually that Klaus mentioned this one already, but I will go one step further in his description. Let's say So here you see, so what Kater did is record this quadrature again in time, and then what you can do is plot the integral of this quadrature from time 0 to time t. And in this particular case of the measurement of sigma z, and if there is not too much decoherence, taking the integral is a very good indicator of where you are on the blocks here. So it's possible to go from this integral quantity and the information about the starting point on the blocks here and compute with a stochastic master equation such as the ones that Pierre Rouchon described. You can compute the density matrix at any time. And so here you see what's done in this experiment is that for one particular trajectory, you can stop at some point. And as Klaus described, if you want to test whether this trajectory is well predicted, so whether this value of Vm indeed predicts a given rho of t, what you need to do is use many trajectories that are predicted to end up on the same state, and do the tomography on of the qubit by a projective measurement of sigma x, sigma y, and sigma z after all these trajectories. So it's a huge post selection, but with that you can do this kind of curve where so here you compare the prediction of the stochastic master equation on a single trajectory with the which is in dots, I guess, yeah, and with the measured one, which is the result of this tomography protocol. And as you can see, the match is very good. Okay, so the final experiment I'd like to mention before going to part 2 is this one by the Yale group. So here is a picture, a movie. You will see a movie of the measurement process. So here is again these histograms that I've been showing as simply a disk. So here is an actual measurement. So it's a 2D histogram. So you see a Gaussian function here from the vacuum state. But now if we turn on the amplitude of the drive and start in the superposition of 0 plus 1, it's actually 0 plus I1 in this experiment. So you see that indeed these two blobs start to separate, revealing that we go from a weak measurement to a projective strong measurement. And beautifully, it's possible to do again the tomography of the qubit condition on where we are in this phase space. So this is what they did here. So here again, they start from this plus y state. So the 0 plus I1. So you see here each point. So for each point here, they do a qubit tomography and measure. So let's say so you see if I'm at the point here of my pointer, so you see it's red, which means that many experiments that measured that value for I and Q had an average tomography of sigma y, which was close to plus 1, which is expected because we start from plus y. And here you see that if they measure x, well, it's more or less white, so 0 sigma x. So sigma z is a bit towards the blue, and this is because of decay during the measurement. So now if we turn on the amplitude, you will see a movie again where these colors change completely. So you see maybe I will play it again. So the first evident thing we see is that sigma z is now strongly correlated to the position in the phase space. So if you're on the left, you see that the qubit is in the ground state. If you're on the right, the qubit is almost certainly in the excited state. But check out also the back action on the measurement on the sigma y. So sigma y started completely red and now it's white. And so if I play again this movie, maybe notice the separation of between the two blobs when these colors start to appear, right? You see it's right, that's here, right? So here, so the two blobs are very weakly separated, but that's already enough to to qualify this measurement as a non-weak anymore. Okay. So to sum up this first part, so the reason why quantum circuits are good for superconducting circuits are good for quantum trajectories. So the coherence times are now very, very long. The error probability is very low. It's possible to tune the readout rate and to channel out the emission and the measurement signals into microwave lines. And we also have quantum limited amplifiers, which are essential to observing this kind of trajectories. Okay, so that concludes the first part again. So what I'd like to do now for the second part is to do it on the blackboard. So let me see. Yes. Okay. So now that we have seen how the superconducting circuits work. So we've described a bit this dispersive Hamiltonian and how it can measure in a QND manner sigma z. I'd like to describe a bit better what's this. So precisely to answer the kind of questions we had about the discreteness of the measurement or not. Yes, question? Yeah, sure. Yes. Yes. Exactly. Yeah. Ah. Mm-hmm. Yeah. Yeah. Good question. So microwave sources have a precision which is absolutely extraordinary. So it's below the millihertz for the source, right? For the source. Now, if we want to characterize this number precisely, you see this cavity is well coupled. It's a readout resonator. We want a lot of information per second to get out. So we need to couple this resonator well to the environment. So the line width of this cavity is actually quite large. It's 10 megahertz. Or the good situation is when it's comparable to chi or over 2 or square root of 2. I can't remember. So because of that, we are not really limited by the precision of the measurement, but more by the fact that the line width is large, and so it's not necessary to know many digits, given that the line width is 10 megahertz or so, right? Now, for the qubits, when the qubits have coherence times which are now above 1 millisecond for transmit, then we can do a Ramsey interferometry to determine very precisely the frequency of the qubit. So the number of digits is quite large. It's we know them to better than 100 hertz, something like this. This is yes, and the 4 megahertz. So this is a bit more involved. So we can do. So there are experiments where we can populate the cavity and do Ramsey interferometry while it's populated, and then there are revivals in the Ramsey spectrometry that pinpoint very precisely chi. So this is one of the best techniques to measure chi. The number of digits again, it's not that good, right? I would say maybe we have 3 digits, something like this. Other questions maybe before I move on? Right? So okay. So in the 20 minutes that are remaining, I would like to tell you how we model these measurement apparatus. And maybe before modeling the apparatus themselves, we need to understand how to model the modes, right? So the propagating modes that arrive on these this measurement apparatus and that couple to the quantum systems. So there's a good article, I think, on this by Roy and Devoret. Archive. Ah, so it's cut. Okay, interesting. Ah, no, okay, so the screen is, I see. Okay, sorry. Ok, c'est embêtant. Okay, maybe I'll do it on the actual Blackboard. Give me 30 seconds to try it out, and otherwise we go on the Blackboard. Okay, let's not lose our time. So, okay, so right. So we'll just write on the Blackboard. Okay, so yes, I was saying a good review for this is Roy Devoret, archive 1801 115, and also the thesis of Hector Hutin, one of my students. Okay, so what's a propagating voltage? Ah, yes, it's hard. Okay. So propagating voltage. So what we're going to do is try to understand how to describe the modes that live in these microwave cables, and so one way to do it is to model the microwave cable by a series of inductors and capacitors. Okay. So these in this model, so this step would be a tiny distance dx. The capacitor would be a linear capacitor, linear capacitance C, and the inductance would be a linear inductance L, such that the infinitesimal inductance is L dx and capacitance is C dx. So that gives us two characteristic numbers. One is a square root of L over C, which is the characteristic impedance of the line. And the other is the speed at which light propagates in the line, which is 1 over square root of LC. Okay. So then we want to know the states of this line. So what we're going to do is define the current I of x and t and the voltage V of x and t that lives across the capacitor. So you see that we will have a voltage that depends on the position and on time, and so then from there we can define. Is it large enough? Ouais, thanks. So we will define this voltage at a given point as the sum of two terms: a voltage propagating to the left of x and t, and a voltage propagating to the right of x and t. And the rule to distinguish the two, so one is propagating to the right, one to the left. So basically, the distinction between the two is that So they are both a function, which by abuse of notation we write with the same name. So v left or right of time minus or plus x over vp. Okay, so I think it's clear for everyone. So we now have this function that characterizes the fields propagating to the right or to the left. Okay, so this time and position hybrid, I will call it tau, tau minus or tau plus, depending on the direction of propagation. So the voltage, we can take its Fourier transform. So the voltage left or right, we take its Fourier transform, so we will define it with the square root of 2 pi. So from minus infinity to plus infinity of v of t. So we have tau, sorry, left or right, exponential plus I omega tau d tau. And so with this, we will define the amplitude, which we will now put a hat on. So the complex amplitude, which is analogous to somehow an annihilation operator, as you will see, that corresponds to left-moving or right-moving waves, is simply defined by a square root of 2 over h bar omega zc, characteristic impedance, times the voltage operator, this propagating voltage operator. Okay. All right. So with this definition, you see quickly that if we take this amplitude operator at a minus omega, the minus will enter here, and so this will be a dagger at the positive frequencies. So actually, right or left of minus omega is a dagger right or left at plus omega. Okay. So because of that, the commutation relation between a omega and n omega and a omega prime is a bit disturbed. And this is the source of many issues, but we will do an approximation soon so that we don't have to deal with them. So but formally, the annihilation, the commutation relation between annihilation of right or left and annihilation of and creation right or left of omega prime. So this commutator, it's delta of omega minus omega prime, which we would be happy with. But there's also the sign of omega, which comes here, which is due to this fact. Okay, with the same for the left propagating waves. Okay, so from there we can go back in the temporal space. So we can define A of tau, again right or left, as the Fourier transform of this. But here there are several conventions that we can use. I mean, not several, but a few. And what we're going to choose here is to integrate between times 0 and plus infinity. So from 0 to plus infinity, of exponential minus a omega tau d omega. Okay. So if I write the commutator of a of tau and a of tau prime, it won't be nice. There will be a delta of tau minus tau prime, but then a principal value of 1 over tau minus tau prime. So let's not do that and jump quickly to what's physically reasonable. So we will do the limited bandwidth approximation. Okay. Yes? Yes, so one of the tests would be that one of the tests would appear in the quantum when we will look at the quantum limits of amplification, for instance. So then it will clearly appear that it's because the commutation relation here is not zero, that there is a minimal amount of noise that an amplifier needs to add. But there are, yes. Yes, they would commute, absolutely. Yeah, right and left, they commute. Yes. Okay. So the main issues we have with this sign and the fact that here the commutator is really useful, they come from the fact that at omega equal to 0 we have an issue. It's hard to basically work with both sides of the spectrum. But in practice, this is not really an issue because of there's always some finite bandwidth anyway in an experiment. And so what we're going to assume now is that there's some. So if I plot the spectrum of the signal, so the actual occupied frequencies by the signals of interest as a function of omega, and here I have trouble describing what I mean, but it's let's say the spectrum vaguely. So we can have, of course, some structure, but what we're going to say is that there will be some frequency omega naught and some spread delta omega, and which are such that delta omega is much smaller than omega naught. Okay, we're going to say that delta omega is much smaller than omega naught, and in this way we avoid many issues with this. We can forget the sign. So it's much easier. Okay. So one of the direct consequences of this assumption is that we can write we can link the voltage operator. We can see it as simply one of the quadratures of this A of t operator, which is the basis of what I discussed in the previous talk. So let's try, right? So we have a V right left of tau. Is it possible to remove the screen? Let's see. Sorry. Okay, I'll continue. So V right left of tau. So you see V right left of tau is if we look at the definition of A. So A is the Fourier transform of this V up to a factor. Yeah, thanks. And maybe turn off the beamer. Thanks. All right. Okay, so it's ZC H bar over 2, but we will have this square root of 2 pi, so it will be a square root of 4 pi now, and then we have we will you see the issue we have to deal with is that there's an absolute value of omega in this expression, so we will have to cut the Fourier transform in 2 parts, right, for positive and negative frequencies. So for positive frequencies, we have a square root of omega A right or left of omega, exponential minus omega tau d omega, plus, so now for the negative frequencies, so we have integral from 0 to plus infinity, square root of absolute value of omega, so which becomes omega, A right or left of omega dagger, because A of minus omega is A of omega dagger, exponential I omega tau d omega. Okay. And this is where we're going to use this limited bandwidth assumption, because you see because of the limited bandwidth, what we're going to do is called the Wigner-Weisskopf approximation. So we're going to essentially say that the omega, which is here in the integral, we're going to say that this is more or less omega naught. Okay. So we're going to take it out of the integral now. And you see that this is now simply the integral of this term, so which is simply the Fourier transform of A and of A dagger. And so in the end we get, so it's approximatively equal to square root of ZC H bar 4 pi omega naught times this Fourier transform. So it's so there's a 2 pi which I need to eat, and so we have a left right of tau plus a left right dagger of tau. Maybe I should put the dagger here. Okay, that's it. So you see that under this approximation, things get simple, and we link directly the voltage that we measure, on which I should put a hat, to the quadrature. So that's one quadrature of the propagating mode. Okay. All right. So in the time remaining, I will precise a bit better what are these modes I've been mentioning since the beginning. Okay. So let's say we want to create one excitation, one photon in one of these modes using these operators. So it's possible, for instance, to consider this operator acting on the vacuum of the line. The vacuum of the line is everything in the line is at the minimal energy. So if we apply this operator to the vacuum, we create one excitation which is localized in time, infinitely localized in time actually, at time tau. Reciprocally, it's possible to create an excitation which is infinitely localized in frequency. But both these quantum states are actually unphysical because they are infinitely precise, either in time or frequency. So this is not something that's actually possible in reality. So to solve this problem, what we need to consider now is so it's a bit like actually if you wish, it's a bit like the eigenstates of the position operator in quantum mechanics, you know, which are not properly defined and not physical. But we can solve this by introducing let's say the wave function of the mode, but it's a very classical thing. So f of tau would be a function of L2 of R in C. So it's a function which has a finite integral when squared. And actually, we are going to even consider that it's normalized. So we say that this is 1. So then we can define a new operator, which would be so I'll call it AF. So AF would be the weighted average of these annihilation operators A of tau, weighted by the function f. So it would be f of tau star A of tau d tau. And actually, this by the power of the Fourier transform, this is exactly the same as f as the Fourier transform of f times A of omega d omega. Okay. So the properties of this AF are much nicer than the properties of the A of tau and A of omega. In particular, the commutation rule. So AF dagger is just 1. There's no delta of t minus t prime or anything. It's we come back to a regular annihilation operator of a harmonic oscillator. So it's just 1. And likewise, if you look at the commutator between AF and AF, of course it's 0. What's a bit more interesting is if you look at AF commutator AG dagger, where G is another function which is in L2 over C and of norm 1. Then this is simply F scalar G times identity. Okay, F scalar, the scalar product here is taken under this, this distance here on L2, so the integral of Fg. Okay, so you see now the interpretation is much simpler. So AF dagger on the vacuum is one photon in the electromagnetic mode defined by F of tau. So the shape, if you want, one way to see what we're doing is saying that we first solve the Maxwell's equation. We define eigenmodes of these solutions, and so these define waveforms or wave functions of these modes. And with this tool we have described, it's possible to populate these modes or work on them in a second quantization approach like this. And just to conclude here, one way to interpret this, so the square of f of tau when we prepare this state is the probability to measure, to observe, let's say, to observe a click at time tau with a perfect photodetector. At time tau, at a photodetector at x equals 0, at the position x equals 0. Okay, so I think it's time to stop here. So tomorrow we'll see how to use this to characterize homodynamic heterodyne detection and amplification.
Thank you very much, Benjamin, for the lecture. Now is the time for question. Does the audience have any question?
So why are you not doing this? Why are not these modes orthogonal? So why are not the normal modes orthogonal? Why are you taking non-orthogonal modes?
So here I'm considering any function g, but actually you're absolutely right. If you want to quantize the line properly, you indeed introduce an ensemble of orthonormal basis of L2 over C, and you can work with this. There's actually a recipe I'll mention at the beginning of the next lecture, how to determine what is the best eigenbasis for the problem. So by doing by doing some diagonalization.
So in an experiment, if you wanted to create a certain single photon, yes. So how exactly would you input to this function f of t, or how would you do it?
Yeah. So one way to create this state experimentally, if f is not too dynamic, has a reasonable spectrum. One way is an experiment in which you do this. So let's say there's a cavity coupled to a qubit, and so for this I will need a Chetrite actually. So 3 levels. The output here would so the output would be coupled by so it will be coupled at a rate gamma to the outside world, the cavity. But the qubit is very long-lived; it's not coupled to the outside world. And kappa will be a large scale in the problem. It will be much larger than the typical bandwidth of which I call delta omega here, bandwidth of the function f. Okay, so we start from this. So what you can do is excite the qubit in you can excite the transmon in this state 2, and then what's possible is to send a wave at the frequency omega 0,2 for the qubit minus omega cavity. Okay, so if I send a wave like this, I will activate a parametric term, which will convert this excitation 2 into a 0 state and 1 photon in the resonator. Okay, so this again would go from state 2 in the Q-treat, 0 in the cavity, to state 0 in the Q-treat, and 1 in the cavity. So yeah, okay. So now to answer your question, this drive, it's exponential I omega times t times some amplitude. Well, this amplitude will be the function f of t. So if you drive with an amplitude f of t, it's possible indeed to release this single excitation of the cavity with an envelope in the line, which can be arbitrary, and which is simply given by this prefactor. So this is one possibility. This was in the classical signal you send with a drive. Yes, absolutely.
Yeah, I have a question about the measurement of quadrature. Do you measure the imaginary part or real part at each time, or it's some kind of heterodyne measurement?
So this will be either homodyne or heterodyne, and we will discuss that tomorrow in detail.
All right, last question there.
So how did we reach this interpretation that mod of f tau square is the probability to observe the click at a time tau?
Yeah, for now we did not. We don't have the tools yet, but if I want to give you a simple teaser, the observable for the photon detector is a of tau, a dagger of tau, a of tau. So indeed, if you want to look at the probability to find a given eigenvalue here, it will be given by the Born's rule.
Okay, so this makes sense when you have defined that capital AF,
yeah.
And if I take a dagger, okay, it'll return that to me.
Yeah, if you write that this is the observable and apply Born's rule on that state with this definition, you will find this.
Thank you.
I think we can thank the speaker again. And we meet back in 15 minutes?
4:20.
20 minutes, so 4:20.